The fundamental theorem of line integrals naturally follows from the first fundamental theorem of calculus, but when I first learned it, it took me a while to fully understand it. The proof that I first encountered felt like clever algebraic manipulation, without any motivation or understanding. But hidden behind a series of algebraic rearrangements lies an intuition that anyone familiar with the relevant concepts can grasp. First, a refresher on a few basic concepts in multivariable calculus. Let f be a function that takes in points in space and outputs scalar values. For example, it could be the case that f of 1, 2, 3 equals 7, or f of 3, 6, 1 equals 9. Now remember that the gradient of f, denoted by an upside-down triangle, is a function that takes in points and outputs the vector partial f over partial x, partial f over partial y, partial f over partial z. Let's say I had a short curve in space whose endpoints are a and b. Let's also say we want to approximate how much f changes by moving from a to b. That is, we want to approximate the value of f of b minus f of a, and all we're given is the gradient of f at a. How do we do this? Well, imagine if moving from a to b involved only changing the x-coordinate of our position. Then we could approximate f of b minus f of a by multiplying the distance traveled, delta x, with partial f over partial x. This approximation is exactly what partial f over partial x is designed for. It expresses what happens to f when we slightly change the x-coordinate of our input. Algebraically, it's the limit as delta x goes to 0 of delta f over delta x. Similarly, if only y or z were changed, the change in f would be partial f over partial y times delta y, or partial f over partial z times delta z, respectively. But in the actual situation, all three of x, y, and z are changed as we move from a to b. We're interested in how this affected the value of f. The 2 points displayed on screen between a and b are intermediate destinations between our initial and final positions if we were to do the following in sequence. Change only x, then only y, and then only z one after another. We can see how much f changes during each step of this journey, and then add together these changes to get the total change. When we go from a to the first point, the change to f is approximately partial f over partial x times delta x. When we continue to the second point, the change is approximately partial f over partial y times delta y. And when we go from there to b, the change is partial f over partial z times delta z. Together, the total change when moving from a to b is the sum of these three component changes. Here we are expressing the change to f as the sum of each change caused by movement in the x, y, and z directions. We can helpfully write this approximation as the dot product between the gradient and the displacement vector. The displacement vector is just the vector that connects a to b. An important assumption here is that the gradient changes negligibly as we move along the curve, because f and its partial derivatives are continuous. But our expression for the change to f is only an approximation. The gradient is actually changing continuously along our curve. It would be better if we cut the curve AB in half, determined the gradient at a and at an intermediate destination, and added the two approximations. This would still be imperfect, but less so. You can probably see where this is going. To precisely determine f of b minus f of a, we split the curve between a and b into an arbitrarily large number of pieces, and add the sum of each small approximation to get the total change. It should be intuitive that our approximation grows more accurate as we increase the number of component approximations, and we more closely track the changes to the gradient along the curve. And in the limit, the approximation becomes exact. Algebraically, instead of our sum, we have an integral. This is the fundamental theorem of line integrals. Both the fundamental theorem of line integrals and the fundamental theorem of calculus for single variable functions capture the fact that a total change between 2 points is simply the sum of many component changes. There is a close visual and conceptual resemblance between these two facts, and the multivariable version follows naturally and intuitively from the single variable one. Those familiar with physics might notice an interesting connection between the fundamental theorem of line integrals and the path independence of the work done by a conservative vector field. This is a topic for another time, though. Anyways, thanks for watching.